Okay, I want to talk just now finally about a variant of this. So Hamilton had a friend, John Graves, that he corresponded with quite a lot. And Graves, when he heard about quaternions, complimented Hamilton and said, this is all really great, but what about, can you go further? Can you go to, say, 8 dimensions? We're going from complex numbers, going from real numbers to complex numbers, we're multiplying by 2. Going from complex numbers to quaternions, we're again multiplying the dimension by 2. What about multiplying by 2 again and going to an 8-dimensional arithmetical system? And so Graves started working on this, and a few months later he discovered, in fact, an 8-dimensional arithmetic. And these things are called octonions. And they're usually denoted O. By the way, quaternions are usually denoted H in honor of Hamilton. Okay. So we have this sort of system, Q, C, H, O, or Q or R, if you believe in real numbers, which I don't, but okay, you no doubt think you do. All right, so in each case we're sort of multiplying by 2. And the octonion arithmetic is a little bit more complicated because it's 8-dimensional. So not only do we have an identity, we have an I, J, and K, but now we have 4 more things, L, M, N, and O. And then it turns out that the multiplication can be kind of encoded in the following diagram, pleasantly. So we put an O here, a J here, an M here, a K, an N, an I, make an L, make a circle here, and we put arrows. That way, that way, that way, that way, and this way. Okay, and this funny-looking diagram, which has these 7 nodes corresponding to these 7 here, it tells you how to multiply any 2 of these things. So first of all of them square to -1. So I squared equals J squared equals all the way up to O squared equals -1. And if you want to multiply I times K, what you do is you find the line that contains I and K. Okay, there's an I and there's a K. So the line that contains I and K in this diagram is this line here. This is also a line. And that line then contains a third point, namely J. And if we're going from I and multiplying I times K, we get J but with a minus sign because we're going against the flow of the arrows. So I times K would be minus J. Or for example, J times M would be O, because along here, J times M would be O. Okay, so then there is this is an arithmetic which is no longer commutative, not commutative, and in fact it turns out to be also not associative either, as Hamilton observed. So we're losing not just commutativity, but we also lose associativity. But we do have a sum of squares identity. In other words, it is true that if you have 2 numbers which are the sum of 8 squares, then there's a formula that you can use to write the product as a sum of 8 squares, which is in the same spirit as Euler's formula, but has 8 squares in each term. Okay, octonions were also, in fact, independently discovered by Arthur Cayley, who was a very prolific English mathematician around that same time. And there was a bit of dispute about priority because Graves didn't get published quite as promptly as he should have. In any case, octonions have never really played as big a role in physics as the quaternions, but surprisingly, in recent decades, it's become known that octonions do have a very interesting connection with something, a big symmetry group, let's say, called E8. So there's a big symmetry group. Physicists are very interested in symmetry groups, and there's these various families of symmetry, simple Lie groups, and E8 is sort of the biggest exceptional Lie group, whatever that is, and it turns out that there is a very interesting and subtle connection between E8 and the octonions of Graves. So they're not out of the picture yet, and they still may play an interesting role in our understanding of modern particle physics, because there are people who think that E8 is important for understanding modern physics.